Okay, so this is Adam, and I will be doing sections 1.3 on accuracy, precision, and significant figures. And also, I will be doing section 2.4 on acceleration. Now, starting right off, accuracy is how close a measurement is to the correct value for that measurement. For example, let's look at this bullseye. Now, the bullet holes are rather close to the bullseye, but not close to each other. So therefore, this would be accurate, but not necessarily precise. On the other end, precision is how close the measures are to each other. Let's look at this bullseye. See, the bullets are very close to each other, but not close to the bullseye. Therefore, this would be precise, but not accurate. So instead, let's take a look at one that is both. See, all the bullet holes are very close to each other and are in the center of the bullseye. So this would be very accurate and very precise. Now, part of measuring is uncertainty. Now, uncertainty is a quantitative measure of how close the expected value is to the value that you measured. Now, uncertainty isn't necessarily a good or bad thing, but usually it tends to be on the worse side of things. A measure can be uncertain because of the limitations of the measuring device, the skill of the person making the measurement, irregularities in the object being measured, as well as a handful of other factors. Now, percent uncertainty is a way of putting uncertainty into a percentage so that everyone can understand it. It has its own equation where squiggly sign A over A times 100 is equal to the percent uncertainty. Now, the top value is the degree in uncertainty in the measure, and A is the value of the measure. Let's give it a try with this practice problem. Time intervals measured with a stopwatch typically have an uncertainty of about 0.2 seconds due to human reaction time at the start and stop moments. What is the percent uncertainty of a hand time measurement of A, 5 seconds, B, 50 seconds, and C, 5 minutes? So plug for A, we start by plugging 0.2 in as the top value and 5 in for the bottom value. Now we plug this into a calculator and we 0.04. Now this is a decimal and we need to get this into a percentage, so we would multiply by 100 and this would equal 4%. Moving on to letter B, we have the same value for uncertainty, but now a larger value for A. So we plug that into our calculator, and we get 0.004. And if we multiply that by 100, we get 0.4%. Lastly, for part C, we have 5 minutes. Now this is in a different unit, so 5 minutes is equal to 300 seconds, and the uncertainty remains the same. Plugging that into our equation, and then into a calculator, we get 0.00067. Multiplying that by 100 to get our percent, we get 0.067%. So we have our three answers. As you can see, the uncertainty stayed the same, but the actual value grew larger and larger, and therefore we got smaller and smaller numbers for percent uncertainty the more time there was. Next in the section is significant figures. Now, significant figures can help tell us how accurate or precise measurement is. By its rules, the last digit in a significant figure is the first digit with some uncertainty, and is usually rounded. So here we see a set of rules for determining significant figures. Number 1, every non-zero digit is significant. Zeros in between non-zero digits are also significant. Zeros at the beginning of a number are not significant. Zeros that fall at the end of a number and after the decimal point are always significant. And when a number ends in 0 but does not have a decimal point, those zeros are not significant. So let's go over a few practice problems now that we've had those rules. Number 1, we just do the number 1, 2, 3, 4. There are 4 significant figures. The second problem has zeros at the beginning, which as we learned are not significant, so therefore it only has 2 significant figures. Number 3 ends in a 0, and there's no decimal point, therefore that 0 is not significant, and there are only 2 significant figures. Number 4 also ends in a 0, and has 4 numbers before it that are not zeros, and therefore they are significant in the 0. And finally, number 5, it ends in a 0, but is after the decimal point. Therefore, there are 5 significant figures. And that is all there is for this section. Okay, this is section 2.4 on acceleration. Acceleration is the change in velocity over time, and average acceleration can be found by using the following formula. Change in velocity over change in time. Now, because velocity is expressed in meters per second and time is also expressed in seconds, acceleration is usually found as in the form meters per second squared, or meters per second per second. Now, acceleration is also a vector because it uses velocity, which is a vector itself, and therefore acceleration is dependent on direction. So because of that, let's take a look at this diagram of a car. Now in A, the car is accelerating and has positive acceleration. In B, the car is slowing down and has negative acceleration because of its direction. In C, it has positive acceleration, but because of the direction it's traveling, it is slowing down or decelerating. And finally, in D, it has negative acceleration, but it's speeding up because that's the direction that it's traveling. So let's try to do one by ourselves. A car drives due east from a stop to 100 meters per second in 2.66 seconds. What is the acceleration of the car? So we can go ahead and take a look at our equation, and we see that it's still change in velocity over the change in time. Now because it goes from a stop, the initial velocity would be 0, and its final velocity would be 100 meters per second. So our equation will look something like this. Now all that's left to do is plug it into a calculator, and we get 37.6 meters per second, or meters per second squared. Now let's try one more example. Okay, so this problem reads, a car driving east at 75 meters per second skids to a stop in 4 seconds. What is the acceleration of the car? So let's bring in our handy-dandy equation again. In this case, the final velocity, because it goes to a stop, is 0, and the initial velocity is 75 meters per second. So plugging that in, we end up with negative 75 meters per second over 4 seconds. Plugging that into our calculator, we see that the value is negative 18.75 meters per second squared. This makes sense because the car is decelerating, so the acceleration would be negative. Now applying significant figures, because the rules of significant figures, we would end up with negative 20 meters per second squared. And that is all for this video.